Hello guys, today we will be going over DFS or depth first search and its implementation in Python. Okay, so namely there are two graph traversal methods, that is DFS and BFS. We will be covering DFS in a later video, but today we will be seeing what a depth first search is and how we can implement this in Python and what does it actually do, like why would we implement this, what are its benefits. So we'll also see a very small application of it. So yeah, now let's come to the DFS definition. So this is the DFS definition from Wikipedia, you can check it out. So what it says is DFS or depth first search is an algorithm for traversing or searching tree or graph data structures. So as I said you, this is a graph traversal method. The algorithm starts at a root node. It starts at the root node for a tree, and it can start at any node for a graph. Okay, so and it explores as far as possible along each branch before backtracking. So what this essentially means is, if I call DFS upon node A and node A has connection to node B and node C, the DFS function will go to node B, and then it will forget about node A and all of its rest of the connections. Its primary focus will be to explore node B. So right now it will be exploring node B, and once when it's done it will come back to node A, and then from there it will go to node C and so on. Okay, so let me just show you. So this is a graph that we have over here. This is an undirected graph, so this means a connection from node A to node B is also a connection from node B to node A. Now let's see, we want to traverse the entire graph, right? So let's say we start from node 0, since this is the most left one, but that doesn't mean anything. You can start DFS at any node that you want. So let's say we start our DFS from node 0. So node 0 has connection to node 1. So from there this will go to node 1, right? And now node 1, it will see all of the adjacent connection of node 1. So node 1 has connection to 2, node 1 has connection to 3, to 6 and to also 0. So node 1 should go to 2, right? But see, here's the problem. The computer does not know that we have already come from 0, the node 0. So actually we will be here stuck in an infinite loop where we would be just going here and there between node 0 and node 1, because he doesn't know that from where we came from, right? So this should give a hint that we need to keep track of the nodes that we have already visited. So yeah, we will do that. So now, but for simplicity's sake, let's say we are at node 1, and from node 1 we know we have crossed 0, so we won't go there. So from 1 we can go to 2, to 3, to 6. Now you can go to any node that you want, it's completely up to you, and also in the order that you store the nodes. So let's say we go to node 2. So now we are at node 2 and it will explore all of its adjacent connections. So node 2 has only connection that's to 1. So should it go back there? No, we have already visited 1, so it shouldn't. So our DFS for 2 should end right here, and from there we would trace back to node 1, and now 2 have been visited. So from node 1 we would again call our DFS and it will go to these adjacent nodes. So right now let's say we have 3, so we will go to 3 and then it will see all of the adjacent connection for 3. 3 has connection to 4, to 5, to 6, to 1. 1 have already been visited, so let's say it will go back to node 5. So when it goes to node 5, it will see that we are at node 5. Okay, so node 5 has connection to 3 and to 4. Okay, so it will go to node 4 because we have already visited 3, right? So when we are at node 4 has connection to node 3, to node 5, to node 7. Since 3 and 5 are already visited, from node 4 we will go to node 7. Now we are at node 7. So it will see all of its adjacent connection. Node 7 have connection to 6, node 7 have connection to 4, but 4 is already visited. so we would go to node 6. Now while we are at node 6, we will see all of its adjacent connections. So node 6 has connection to node 1, to node 3 and node 7, but you can see that we have already visited all of these nodes. So what do you think will happen? We will trace back from 6, we will come to 7, so we will just come back. From 7 we came from 4, so we will go there. From 4 we will go to 5, and from 5 we will go to 3, and from 3 we will go to 1, and from 1 we will go to 0. And this is how our DFS traversal ends. Okay, so this is pretty simple. Now let's see how we can code this out in Python. So yeah, so these are the inputs, these are the sample inputs that I have kept there for the graph that we just saw, and we will be seeing how to implement DFS using an adjacency list and also adjacency matrix. We will cover both of them. So firstly, let's say we are going to do it with adjacency list. So as you can see here, we have our class, this adjacency list. So this is our adjacency list, and yeah, so and if you have not seen how to implement them, you can go and check my last video where I have told how to implement adjacency list and adjacency matrix in Python. So yeah, let's get started. So let's define our function DFS, and as I told you before, we can start from any node. So let's give it something like node, any node. This can be any node, literally any node. And now what we need to do is, as I told you before, we also need to keep track of the nodes that we have visited. So let's make a visited array which will contain false, values. So every time we visit a node, we mark it as visited or true, right? So let's say we make an array visited and we initialize all of its value with false, and there will be nodes plus 1 values because it starts from 0. So the moment we call DFS on a node, we would essentially mark this node as true, since this means that we have visited this node, right? And now what we would do is, we would essentially go over all the connections that we have for that node, and we will be calling DFS upon them if they are not visited, right? So yeah, but before that, let me just show you how the connections look like. So let's say we are calling our graph, yes, and let me just show you the adjacency list. In that way it will be more clear for you, I guess. So let's say grp equals to graph.returnGraph, and we'll just print it. So print grp. Okay, so, and as I told you, this is an undirected graph. So yeah, now see, these are all the connections that every node has, right? So let's say we call upon node 0, or let's say we call upon node 1, whichever. So this will go to all of the connections that node 1 has. So we will need to access this list, and then we need to access all of the elements or all of the nodes that this list has one by one, and we would be checking if it's visited. If not, then we would be calling DFS upon this, and if yes, then we would just move ahead. Okay, so this is the way in which the nodes and the connections are represented. So just something to keep in mind. And now for I in range length of grp of node. So grp of node just means that node. So let's say we call grp of for node 1, then this would just mean that this entire node and the length of it is 4. So we would be iterating over this, and let's say we make something as current node. So our current node would be grp of node of I. So what this basically means is, so this for loop, this starts from 0, right? So let's say we are at 1, so when we call it from 0, so this grp of node would access this list, and this I would access the ith index element. So for I equals to 0, it will access 0, then for I equals to 1, it will access 2, and then for I equals to 2, it will access 3, and so on. So these are going to be our node. So we will check if visited of current node is equals to false. So this means the current node has not been visited. Then what we would do is we would call DFS upon our current node, and that's it. We are essentially done over here. Okay, we are essentially done, and now let me just show you the working. So let's say I'm going to print every node that we visit, so we know how the traversal actually works. And let me just call DFS upon node 0. Okay, so we are calling DFS upon node 0. So let me just get you through the process once. So initially this will be all false, 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 false. So how many are there? 1, 2, 3, 4, 5, 6, 7, and one more. So this is going to be our visited array at first. Now when we call DFS upon node 0, it will go and make, because initially all of them are false, right? So it will first, it won't check for the 0th node at first, because we are just calling it, so it will make it true. So here this will become true. Now it will just print this, and we can just skip this line, it's of no use for the moment. And it will see all of its adjacent connections. So it has only one connection to 1, and we are labeling 1 as our current node, and then we are checking if visited of 1 is equal to false. Yes, it's false. Node 1 has not been visited before, so we are going to call DFS upon node 1. So when we call DFS upon node 1, first thing we will do is make this as visited, so we will make this as true, and then for 1 we would go and check its adjacent connections. So this has 0, 2, 3, and 6, but 0 have already been visited, so here the statement will return nothing. So we will go to 2, and then for 2 this will be false, yes, so we would call DFS upon node 2, and now this will be true when we call DFS upon node 2, and then from 2 we would go to 1, but here we would say that we have already visited 1, so this DFS of 2 does not essentially return us anything right now. So we would come back to this DFS of 1, and at this point we are done with 0 and 2. So we would go to 3, and we would call DFS upon 3. So when we go to 3, so 3 has connection to 1, to 5, to 6, to 4, but firstly what we would be doing is we would be changing it to true, right? So right now we are at node 3, and the connections are 1, 5, 6, 4. So let's say we are at connection 5. So 5 has been visited before? No, it's not. So we will just go to DFS of 5, and we will make it as true. So we are making it as true, and then we would check all of its connections. So there are 3 and 4. So node 3 have already been visited, right? We can see here node 3 have already been visited. So we would call DFS upon node 4, and we would make node 4 as true. Now we are at node 4, right? And node 4 has connection to node 3, to node 5, and to node 7. But we have already visited node 3, and we have already visited node 5. So we would go to node 7. Now we are at node 7, we would make this as true, and node 7 has connection to node 4, and this has connection to node 6. But we have already visited node 4, so we would go to node 6, and we would make node 6 as true, and at this point our this visited array, all of the nodes are marked true. This means we have visited all nodes, but we are at this 6. So this has connection to 1, to 3, to 7, but all of them have been visited. So from 6 we won't do anything, we would just trace back. From 6 we would go to 7, then from 7 we would go to 4, then from 4 we would go to 3, then from 3 we would go to 1, and then we would go to 0, and this is how our DFS ends. So let's just see this once. So I'm going to run it, and let me just get this sample input. And yeah, as you can see, okay, so I just printed the graph once again. Let me just comment this line. So as you can see, first we go to node 0, then we go to node 1 as I told you, from there we go to node 2, and then we go to node 3, and then from 3, see, 1 is visited, so we go to node 5. So we go to node 5, then we check, we see that all of the nodes have not been visited. This 4 node is not yet visited, so we go to node 4, we are at node 4, then we see that 3 and 5 have been visited, but 7 have not been, so we go to node 7, and then from 7 we go to this node, the 6th node, since it's not been visited. Then from 6 we trace back. So this is the basic working of this, and you can see this. Let me just show you something. Let's say you make a stack, okay? So by the way, I just wanted to tell you that this DFS, this working is also based on a stack, okay? So let's say instead of printing this, we are just going to append all of our nodes to our stack, okay? And we would be also printing out our stack after every iteration. So let's say we are printing out our stack, and after the completion we would write print after DFS. We would also print our stack. So, and we would also need to pop elements of our stack when all of them have been visited. So what this means is when we see that all of them have been visited, so we don't essentially enter here, we start popping values of the stack. So you will just see what this is in a moment. See, firstly it was 0, okay, then we go to node 1, so we appended 1, then we go to node 2, so we appended 2, and then we saw that 2 does not have any other connection except 1, and 1 have already been visited, so we trace back and we pop 2. Now we go to node 3, so we append it, from there we go to node 5, and from there we go to node 4, then from 4 we go to 7, then from 7 we go to 6, and then from here we start popping things. So from 6 we start pop 6, then we pop 7, then we pop 4, then we pop 5, then we pop 3, then we pop 1, and finally we pop 0. And at the end we get an empty stack, just how we started. So this is that, and this is how you implement DFS using an adjacency list. Now let's see how to do this with help of an adjacency matrix. So the basic functionality of the DFS would remain the same. So we would be keeping all of this. We would just be changing how we access the elements, right? Because for a matrix it's different. So let me just make a few changes. So instead of AL we would make it AM. So this is my adjacency matrix, and I'm just going to remove this. Yeah, so we are going to remove this and this true group, and we are also going to remove this, and from here we would make this DFS function work for our matrix, right? So yeah, let me first show you how it looks. Okay, so let me just put pass over here, and this GRP, this is our matrix. So let me just print this. print GRT. Okay, so let's just put all of them aside, and yeah, we will get the same value and see we get this huge matrix. So let me just show this to you. This is quite big. So what I'm going to do is I'm just going to press enter and get them side by side. So this is that. This is our matrix, right? Now see, this is the 0th node, 1, 2, 3, 4, 5, 6, 7. So let me just write it beside that so it will be easier for you. So 0, then this is 1, then this is 2, then this is 3, then this is 4, 5, 6, 7. Okay, and let me also write it over here. So 1, 2, 3, 4, 5, 6, and 7. And I'll just comment this out. So we will just comment this, and we don't need this GRP anymore. So see, what do we need to do over here? Now, as you can see, we will first call DFS upon any node. Let's say we are calling DFS upon this node 0. So what it needs to access is all the connection that it has. And now in an adjacency matrix, we represent a connection between two nodes using 1. So if there's a connection between a node I and a node j, then the adjacency matrix at position I comma j would be 1, right? So we need to check for that, and we would also need to get this list of values. So let's say if this matrix, if this is called GRP, then we would need to access GRP of a node. So GRP of 0 would return this list, and then over here we would be iterating over all the values, and we would be checking if it's a 1, because only if it's a 1, then this means that there's a connection. But we don't end here. When we get a 1 for a specific index, let's say I of, this is year 1, but if this for 5, if this had been 1, then if we saw that this is 1, then this means that this is a connection. So we would just check if the ith index, which means the node, if the 5th node is already been visited or not. So if it's not, then we would call DFS upon this, and if it's already been visited, then we would just move ahead. Okay, so let me just show this to you. So for I in range, and I'll put here nodes plus 1, because for every node this has the list which contains of elements of number of nodes, right? So for all of the nodes this will be having 7, since 7 is the number of nodes that we have. So yeah, and what we would do is we would just check if GRP of node, so the node that we are currently in, let's say we call upon 1, so we would just check GRP of node. This would return us this list, this would return us this entire list, and we would check if the ith index, which means that this or this or this, if this is equal to a 1, because only if it's a 1, this means that there's a connection. But that's not it. We also need to check and visited for I. So if this is this, so let's say we call DFS upon 1 first. So we come here, we see that we get a 1 for the index 0. This means for node 0 and node 1 there's a connection. We also need to check if 0 has been visited before. So that's that, equal to false. This means this hasn't been visited. Only then we will call DFS upon this I, right? Because I is the node that we are dealing with. And that's pretty much it. And we should essentially get the same stack, and the same values. So let me just show this to you. Firstly, we would just print all of them. So we would just print node and we'll separate them with a space. And let me just remove this. And we will call DFS upon 0, let's say. So we are calling DFS upon 0. Let me just get this value once more. Keep in mind this is an undirected graph. So for a directed graph you would need to make here a true, because that's how I define my class. Yeah, so let's just print it. See, we get it just like the previous one. We go to 0, we see there's a connection to 1, we go to 1, and then from 1 we go to here, we see that we have connection to 0, to 2, to 3, to and to 6, but 0 have already been visited, so we go to 2. Now we are at 2, so 2 has connection to 1, but 1 have already been visited, so we come back to this one, and then we see we have connection to 3, so we call DFS upon 3. Now 3 has connection to 1, 3 has connection to 4, 3 has connection to 5, 3 has connection to 6. So we see that we have already visited 1, but we have not visited 4, 5 or 6. So now we go to 4, and from 4 we hit DFS upon node 4. So as you can see that this is a slight difference in the way the DFS traversal works for matrix, because it works iteratively, right? So 0, 1, 2, 3, 4, 5, 6, 7. But if you remember, for our adjacency list, this was slightly different, because after 3 we would have went to 5 first and then 4. But that doesn't matter, as I told you before, in DFS order doesn't really matter. Only what matters is when you go to a node, you need to explore that completely. So we get to 5, then we go to 7, and then we go to 6, and from 6 we see that all of the nodes that 6 has connection to have already been visited, so we trace back. Okay, so let me just show this to you once more, that stack.append node, and we would be printing this stack, and after completion of the DFS we would also print that after DFS we would be printing out our stack, so we should get an empty stack. Okay, we didn't pop it, sorry, my bad. We did not pop the values of the stack. So yeah, see, after completion we get an empty stack, just like the one in case of an adjacency list. Now let me just show you a very simple working that we can do over here. Then you just remove this, and let's see, let me just see this. So this, we want to see that if we can reach this node which is not reachable, right? So from 1, can I reach to 3? Can I reach to 3? No, we can't. From 1 we can go to 2, from 2 we can go to 4, then from 4 we can again go back to 2, since this is a directed graph, so the roads are not bidirectional, right? It is to find out the number of connected components in a graph. So the number of connected components means, see, this node 1, this 2 and this 3, they make a single component, right? Since they are connected. Basically a connected component means a subgraph, a subpart of a graph. So here there are essentially 7 nodes starting from 0 till 6. Now 4 and 5 has a connection, so this is a component. Okay, now 1, 2, 3, this is also a component. Now 6 and 0, they are just alone, but they are also individual components. So the connected components for this graph is 4. But how do we do it with help of DFS? Think about it. What we would essentially do is we would call DFS upon every node. Let's say we call DFS upon 0, then we would get nothing, right? So every time we call DFS upon a node and we get out of that function, so basically the function ends, we are going to get a connected component, because let's say we are at node 1 and we hit DFS upon this. So from node 1 we go to 2, now from 2 we go to 3, and now at 3 we see that all of them have been visited, so we trace back, we go to 2, then we go to 1, and then we come back, and whenever we get out of this DFS we have essentially got one connected component. Okay, so let's see how we can do this in code. So let me just remove this tag thing because it's not necessary, right? So I'm just going to remove this. So how would we do this? What we would need to do is the same command would just work. So for I in range of nodes plus 1, this means for every node we would be calling DFS if visited of I equals to false. So this means if the node that's there, if that's not been visited, only then we would be calling DFS upon this I, and every time we come out of the DFS we would be essentially getting one connected component. So let me make something like connected components equals to 0. At first we are keeping it at 0, and every time we come out of this we would essentially increase this by 1, and let's just print the number of connected components. So connected components, as connected comp. Let's see what we get over here. Right, so for this the input is over here, and no, this is an undirected graph, so I need to make a few changes over here. So yeah, and now let's see, we should get our output as 4. See, we have got our output as 4, connected components are 4. So I hope this tutorial was helpful, and if it is, then do give me a like, and I will be posting more such videos about graphs in Python and more coding in relation to Python. So yeah, thanks for joining in, and